This lesson should coincide with the previous lesson on isotope stability. You can learn this one first or that isotope stability first. It really doesn't matter. But what I wanted to focus on in this lesson were the types of radiation that we get and talk about the properties of each as a particle or as an energy wave. So we talked about with isotopes that some nuclei are unstable. They have either too few or too many neutrons in the nucleus. So there's not enough glue or too much glue or just something's goofy. The nucleus doesn't stay together anymore. The nucleus will then change. It'll change the atomic number maybe and create something new. Well, anytime you change the number of nucleons in the nucleus, there's going to be an energy change. Energy is going to be given out to make up the difference in energy between the final and the starting products. So that energy is going to be released in one of two ways. It's going to be given off with the kinetic energy of the particles. Now, kinetic energy is energy of motion. So the particles that are going to be kicked out of the nucleus are going to be going very fast. So they will have high kinetic energies, and that will dissipate some of it. But then there are also some transitions going on where mass is not kicked out, but maybe the quarks in the nucleus or the positioning of the protons and neutrons, they change relative to one another. In other words, their potential energies change. So there's no particle coming out. But when they change their energy values, the difference will be released as a type of EMR. So we may get something on the spectrum. Now, these nuclear changes, these energy values, are usually very high frequency energies coming from radioactive decay. They're going to be more on the right-hand side of the visible light spectrum. The ones that we would call tame would be high UV. But most of the transitions in the nucleus that we're going to get are going to be in the X-ray and then some in the gamma ray categories. So very high energy EMR. So again, there's two types of ways radiation is given off. One is if the energy is giving off in its pure form as the EMR wave, electromagnetic radiation, that is just energy. And the example would be gamma or even X-ray, but those are the two types. Or the energy could be given off as a particle being released with high kinetic energy. And on the screen here I've got two examples, alpha and beta, but then we're also going to talk about two other types, positron, and then a third one that involves the electron. And it's a little different. In a moment I want to put a chart up and we're going to fill it in together, but just to give you an idea here, I'm going to go through alpha and beta. The alpha particle is the same thing as a helium nucleus. So there's two protons and two neutrons. When an isotope undergoes alpha decay, it's kind of like a Jenga tower or a Lego tower that you've built too tall, and now it's so unstable that it's going to fall off. Not just maybe the top block, maybe the top two to four. It's going to fall off in chunks. And that's what happens to the nucleus here. It's blowing chunks to make itself smaller. So the mass of an alpha particle is 4, 2 protons, 2 neutrons, that's 4. And then it's going to have a +2 charge because the 2 protons are going to be charged. The neutrons are not. The alpha particle is actually pretty weak because it's so big it can't be moving very fast. Then we have the beta particle. A beta particle is just an electron. They didn't know that at first, so they called it beta, and then it was later they discovered that they were the same thing. This electron is not one of the electrons in the electron cloud. This is a new one that is created from changes in the nucleus. So it gets kicked out at a very high speed, and it has a charge of -1, like we know the electron does, with essentially no mass. Now we all know the electron does have a mass, but it is so tiny for the purposes of kinetic energy calculations, we just kind of ignore it and say 0. Beta particles are higher penetrating than alpha. Look at this graph. Well, there's the graph. when you compare the penetrating power to alpha, between alpha and beta, alpha can be stopped by something as small as a sheet of paper, because alpha particles, again, are moving slower, but they are bigger and bulkier. It's kind of like trying to drive a truck through a garage door. It's just not going to fit all the time. So some of them will get through, but in most cases, alpha particles are stopped at the surface of whatever they're trying to pass through. Alpha particles for humans cause danger more like blistering, turning your skin red, and damaging just really at the surface. Most humans can survive low-level alpha exposure because your skin will absorb it, again, at the surface, and it'll just kind of slough off. It'll kill that outer layer of skin, and hopefully you can regenerate it. Beta particles are smaller because they're electrons. They can move a little faster, so they have more momentum, and they can pass through smaller openings. So they can pass through something like a sheet of paper, and they can pass almost all the way through your body. They actually won't get stopped until they get, let's just say, halfway through your hand or through your arm or something. So beta is more dangerous for humans because it can go deeper. It can start causing damage to your deeper layer tissues, your endoderms and your mesoderms and things like that, and cause damage maybe to your DNA. It's much more difficult to survive a beta exposure. And then I kind of skipped over gamma. Gamma is pure energy, no mass, no charge. And if we look at this, look how penetrating gamma radiation is. It's just energy, so the wavelength is very small, very tightly packed. It can fit through almost anything. It'll pass through paper, through your hand, through a glass of water, and eventually a thick block of concrete or a thick piece of lead will slow and dissipate the energy enough that maybe it won't pass all the way through. Regardless of what the comic books say, you're not going to survive a gamma exposure. It is extremely deadly, and it basically just tears your DNA into shreds so that the machinery in your biology, in your body, can't overcome the damage. Now let's focus on filling out the chart for all 5 types of radiation. Here's the summary table I was telling you about. These are the 5 types of radiation that we're going to discuss this year. The first, let's get it out of the way, it's gamma. I only put it in there because, it happens, but it's very different. There's no mechanism per se for gamma. But gamma particles, or gamma, is just energy. So you think of it as a wave, and I'm going to put here it's a photon. If we want to think of it as a particle, it's a boson, it's a photon. It does carry some mass, and not almost zero. The symbol for gamma is the Greek letter gamma. It looks like a kind of a cursive, had a little too much to drink, kind of a Y. And then in any symbol for radioactive particles, you're going to put a superscript on the left for the mass. So for the mass of the energy particle, it's going to be 0. And then as a subscript, you're going to put a charge. And for energy, pure energy, a photon, photons have 0 charge. So that is the symbol for a gamma photon or gamma energy. The mechanism, why, it occurs through transitions, and we're going to leave that one as the vaguest. The transitions within the nucleus. Gamma and X-rays really occur with almost every type of radioactive decay. You'll get a little bit of each or both. Which elements undergo this type? More or less all can. We're going to be concerned more with the mass changes in radioactive decay in first-year chemistry, and then the energy changes really need to be discussed at a higher level of physics. And then we have the alpha particle. The alpha particle is one of the easier ones. It is a helium nucleus. There are 2 symbols for the alpha particle. The first one is acknowledging the fact that it's a helium nucleus, so we use He. And then the other is the Greek letter alpha. So it's kind of an A with or a goldfish looking thing. For each of those symbols, we're going to put the mass in the upper left. The mass of the helium nucleus is 2 protons and 2 neutrons, which is a 4. And then the charge, as we discussed earlier, is going to be +2. And then the mechanism for this, why does it happen? It happens when a nucleus is too big, it breaks up. Which elements undergo this type? Large atomic numbers. And I'm going to put on here greater than 83 for sure. That doesn't exclude anything, just in general greater than 83. And then we have the beta particle. The beta particle is a high-speed electron. The symbol then can either reflect the fact that it's an electron and be an E, or we can acknowledge it with the Greek letter beta. In either case, the upper number needs to reflect the mass, and we talked about how the beta particle has practically no mass. And then as an electron, its charge is -1. So the symbol would be 0, -1, and then either E or beta. Why does it happen? Well, this one is a more specific reason. It happens when you have too many neutrons. So as a result, a neutron is converted into a proton. And the result of that conversion gives us a kind of a leftover electron that gets kicked out. Which elements undergo this type? So this is pretty much going to be anything less than atomic number 83. It has too many neutrons, as we learned in isotope stability. All right, all classes of chemistry need to know those first 3. Those are the ones the state of Texas has designated as the big 3. But because we go beyond what the state of Texas wants, we're going to talk about the next 2. Positron decay emits a positron. A positron is the antiparticle, so technically it is antimatter, and it's not that super weird or super rare. It happens all the time. They just don't live very long. Antiparticle of the electron. So what does that make it? Well, instead of E negative, that makes it the E positive. It is the same size and mass as an electron, it just has a different charge, a different quantum number. The symbol for the positron will again be E. It has another one, but we're not even going to broach that one. And then we're going to give it 0 for mass, just like the electron, but this time we'll give it a +1. There's the symbol for a positron. Why does it happen? It happens when you have too many protons. Or you could say that not enough neutrons. So not enough neutrons. What happens is that it's kind of the opposite of a beta. A proton will turn into a neutron and kick out that leftover piece of energy and mass, which is a positron. Which elements undergo this type? Well, these are going to be small nuclei that need neutrons. Usually atomic number less than 20. Again, there's no hard, fast rules to that. And then the final one is electron capture. The electron capture is just what it says. It's an electron. It's the mechanism that makes this one different. So the symbol's the same, 0, -1 for an electron. Why does it happen? It happens when you have, again, not enough neutrons. So nature has come up with a second way to make neutrons, if you will. If the positron emission isn't an option, you can absorb an electron into the nucleus. So it kind of smashes into a proton, and you kind of have the reaction of one proton plus one electron makes a neutron. And that's kind of the mechanism. So the thing that's unique about electron capture is that an electron gets swallowed up by the nucleus, combines with the proton, and it changes the number of neutrons. So which elements undergo this type? These are going to be larger nuclei that need more neutrons. Your intermediate side stuff, atomic numbers 50s and 60s and things like that. Okay, so keep this chart handy. It'll be a good tool as you start writing nuclear equation. You can refer back to it and see what the symbols are and when they might be applicable.